Welcome, sir. Please proceed with the session.
Yes, ma'am. So, shall I continue?
Yes, sir. Please.
So, my screen is visible?
Yes, sir, it's visible.
So, in second session, we will be looking at the role of machine learning in IoT.
Oh, yeah.
So we have actually worked on these particular problems, fault detections in IoT, and home energy management and smart aquaculture management. So we have done some IoT integration into these areas. So let's discuss one of the main problem in IoT network is the fault detections. So we have used a probabilistic neural network for detecting the faults in a sensors. So once you have imagined a smart applications and you have done your deployment with these devices and creating a kind of networks. So there is over a period of time, some sensors may not work, some sensors may behave differently, and some sensors may have a fault and kind of different attacks can also hamper the normal operations of the node. So fault diagnosis is very, very important and crucial, and it is also a very challenging problem in IoT domain. When you will say that device is not operational, when you will say device is anomalous, when you will say the device can create a problem in a network. So kind of different fault may introduce in a network over a period of time. To detect those faults, we have considered a few of the faults. So the fault basically we categorize in 4 categories. One is called hard fault, where the complete hardware is not working. Basically, we will be having a communication between the nodes. And when the node is not operating, it means that it is not relaying any data. It is not communicating with the gateways. It is not communicating with the neighbors. So we consider that there is a hard fault. When device is not at all operating, not at all pinging, not at all doing any communications, then we consider that the entire hardware has a problem. So this kind of fault is called hard fault. Soft fault is basically a software faults, kind of the data that we are generating from the IoT device, and the data which has a same kind of problem like a missing sensor values. Sometimes instances the data will have a lot of difference from the available tolerant limits. So sensors data will have a certain limit. Within that, we can say that data is correct. If it is crossing that threshold limit, the data may have certain faults. So when data will have certain faults, means data will have some error, some kind of problems or errors, we will be considering them as a node failure in terms of software fault. So data which generated by the device is not at all correct, not at all valid data. We consider them as a soft fault. Intermediate fault basically comes over a period of time. Let's say device is working perfectly for some period of time, and all of a sudden some intermediate fault has introduced. Like the device is generating some data, sometime it is not generating. So that the time instance that we are recording, so time series data we are collecting related to the census value. If some point of time the data is not generated, we are considering that the node is under the intermediate fault category. Transient faults are kind of very time short duration faults. They can come for very fraction period of time, like a seconds or 2 seconds. Within that, the device will have a kind of no data or kind of data which is completely invalid. So how to detect those kind of faults? Basically, detecting hard fault is not a difficult task, because if node is not at all responding, we can immediately sense that the device is not working. Data whichever the data generated by the device is not at all coming to the gateway, we are considering that device in the hard fault category. But the other three categories like soft fault, intermediate fault, and transient fault, they are basically time variant. So over a period of time, they may create a kind of problems. So we have to monitor the time series data. So we start recording the census data and analyzing it from the historical data and the current data. What is the deviation? What is the change in the data? And how far this data is valid? That we will define based on the thresholds. So every census will come with its data sheet. So either temperature sensor, humidity sensor, various sensors you have seen, they were coming with a data sheet. You just look at into the data sheet, what are the operating characteristics a sensor will have, when the data is valid, at what different conditions data may create a change in the values, and what is the optimal threshold, what is the tolerant limit within that we say the data is correct. So kind of analysis we can do it by analyzing the data sheet, and those parameters we will be keeping in our program, so that when the data generated by the devices, we keep on analyzing it whether it is crossing the threshold limit or not. That is a one way to detect the fault. Another way is that during a time instance, so over a period of time, let's say for 1 month, we have noticed that data will not be creating any kind of change, like the variation is not very high. But as we moved into the second month, and then the data will start giving certain variations, and sometimes the data is not at all coming. Maybe the communication failure, or maybe the sensor is not producing the data on particular time instance. So kind of problem can come. So software fault, intermediate fault, and transient fault, we are noticing it through the time. If data is not generated, if data is generated, and the time duration basically different for different fault. Soft fault data for an entire period of time is wrong, invalid data. Then we are saying that data is available all the time in the time scale, but data is incorrect. Intermediate faults, the data is generated for certain time period is correct, but certain time period it is incorrect. Transient fault, very few moment the data is incorrect. So you understand that these three type of faults is time variant, and they may have close correlations. So how we can identify which particular category of fault a sensor belongs, like software fault, intermediate fault, or transient fault. So we are analyzing the type of fault. We are identifying the difference between these faults using an analysis of variance. This is an ANOVA in short. It basically helps us to distinguish these categories of fault: soft fault, intermediate fault, and transient fault. And to categorize them in a correct order, we have used a feed-forward probabilistic neural network. It is a kind of neural network which is mostly used in pattern recognition applications and signal processing applications. It is very simplistic neural network model that can be implemented in any edge devices. It is also not taking much resources. So what is the architecture? So probabilistic neural network basically having a four layers. One is an input layer where you apply the input vectors, feature vectors. A pattern layer where you will be training the particular pattern that should be recognized. So if we have a three kind of fault, one pattern layer will detect the soft fault, one pattern layer will detect the intermediate fault, one will detect the transient fault. So according to that, we have to identify what pattern should be kept over this particular pattern layer that can detect the distinct feature that could represent the type of fault. And then we will be taking the average of this summation layer that will be taking the sum of all the individual input vector and corresponding that what could be the average of this particular probability density function, and whichever is dominating, that is basically our decision. So if we are categorizing a three different categories of fault, then three different summation layer probability density function is required. Basically, the operation for this particular probabilistic neural network is based on the Gaussian function. So you can also know with the name of the normal distribution. So when that census data is generated over a period of time, we will be analyzing it with the normal distribution. Whether data is crossing that normal distribution like a bell curve, if data all belongs within the bell curve, we will be saying that data is valid. Whenever it is crossing that limit, we will be saying that data is not fall under this category. So we will be implementing the Gaussian function on each of these particular layers. And then output of these Gaussian functions basically determining the highest average of all be our decision. So let's look at how we have modeled this particular problem for detecting the fault in sensors. So we have used basically normal distribution technique to design the fault model. So we have considered like sensors nodes we have deployed in a different locations for sensing, let's say, kind of environmental pollutions. We wanted to measure the environmental pollution within a city, and we have deployed a distributed node in different places. Now we will be getting the data from these sensors for every time period we are recording, like morning time, evening time, afternoon time. So we have fixed the time durations when we will be going to sense the census reading. So these census reading we are considering, like for the n node, we have n sensor readings, and the time instance is over a period of time. And based on these two input parameters, we have created the Gaussian function that basically calculate the particular distribution in a data. So time is there and the data is there. We will be plotting this data and trying to find out the distribution from the data. So data basically following a normal distributions, then we consider that the data is valid data. Whenever it is going out of that particular variance or standard deviations, then we will be considering that the data is invalid. So considering those failures, like sensor may encounter this kind of fault, we are calculating the variance of each sensor node. So basically fault-free sensor node variation is same, but if faulty node is there, then variance is totally different. So over a period of time, we have historical data and we have noticed that the data cluster was under the normal distributions. And whenever the data is generated next time which is might be a fault, then the variance will be very high compared to the other variance. Then we can distinguish this is a kind of fault. But the basic problem that comes under the fault detection in these three categories: soft, permanent fault, intermediate faults, and transient faults. So if you can look at this diagram, you can understand it, what is this particular diagram is going to give the representations. So normal sensor, if you can see all writes are there, that basically represents the valid data. So the IoT device, let's say monitoring some temperature, and all the time the data is valid. So time iterations, we are monitoring the data. Hard fault, the data is not at all coming from the sensor, and it is very easy to diagnose. So for that, we don't require any probabilistic networks or kind of neural network or machine learning models. But the fault that is more dominant in IoT network is a soft fault, intermediate fault, and transient fault. So soft fault, you can see the data coming from the sensor, but the entire data is incorrect. Intermediate fault, sometimes data is correct, but sometimes data is incorrect. Sometimes correct, then sometimes incorrect. Similarly, transient fault, very less period of time, the data is incorrect, but most of the time data is correct. Now, if you can see from the time iterations, detection of soft fault and intermediate fault is quite easy. But when we taking a consideration of transient fault, it is quite difficult because the time duration between intermediate and transient fault is not very dominating. They may be having a misclassification, like intermediate fault may be misclassified to transient fault may be misclassified as intermediate fault. So when we do the analysis of this particular data, when we do the distribution of this data, this particular data may have the similar variance and mean values that basically determines the normal distribution for the intermediate and the transient. So when there is a close correlation between these two faults, there is a high chance that the fault categorization is kind of difficult. So we adopted a technique called analysis of variance that basically distinguished the data in terms of distribution within the data and with between the data. So hard fault detections, this is what the model that can easily determine the hard faults. Like you have a gateway node and various ZigBee nodes, they are connected and they are sensing some environmental parameters and sending it to the gateway. So gateway is having this particular probabilistic neural network to determine whether the attack or a kind of fault is a cause of this particular misbehaving or anomalies in a node. So hard fault, we already discussed. Hard fault is kind of very easy, that you can easily detect it when you send a request, a hello message, a gateway will send to all the nodes. Whichever node is not responding it may have a kind of fault. So the fault you can determine based on the number of times the acknowledgement you received back from the nodes. So here you can see fault free if there is a no acknowledgement drop. If node is responding back to the gateway, then there is a no fault. If one time it is not responded the acknowledgement, but second time it responded, there is a likely a fault can occur into this particular system. But if multiple repetitions to that particular hello message and no reply and acknowledgement getting out from the data from the node, then it is permanently faulty. So very simple model, doesn't require any kind of modeling or a kind of learning techniques through which we can identify the kind of fault. However, we can model this also in a probabilistic neural network. It's not very difficult. The problem comes in the soft fault detections, because here in soft fault, intermediate fault and transient faults, our soft fault is completely different, but intermediate and transient fault can be misclassified. Because if you can do the normal distributions, if you can see this particular normal distribution, So when you have a data over a period of time and the normal distribution comes like this, like overlapping, then it is very, very difficult to distinguish which kind of fault this particular sensor has. Okay, here you might have some point of distinctions, but if you can see this cross between the normal curve, that will also give kind of error. That could also give us kind of misclassifications. We required a kind of large distinctions. All the normal curves should have a different distinctions. They are completely isolated from each other. In that case, the discrimination is kind of much easier between the fault. Okay. In this category of also very difficult, and our data basically representing this particular category where soft fault detection is much easier, but transient and intermediate fault may have a similar distribution. So to detect whether the distribution will have any difference or not, we will be taking a help of analysis of variance. So it basically analyzes the data and identifying the true difference between the type of distribution. And it basically used two different hypotheses to test whether the data has a difference of distribution or not. So the first hypothesis is called null hypothesis. It basically determines no significant difference between the mean of the sensor. So if null hypothesis is determined, then there is a no difference in between the distribution that transient fault has and intermediate fault has. So it's very, very difficult to distinguish. But alternate hypothesis will give you the at least one significant difference between the mean of the sensor values. So we have to test whether the particular distribution follow the null hypothesis or alternate hypothesis. To determine the ANOVA, to determine the difference in the distribution, we use Anova Steps. So what we initially do, we take the mean of the sensor values of each sensor. So we have n nodes distributed for environmental sensing. They all are generating some sensors data, and we are accumulating all data at the gateway and doing the mean calculation of the sensor value. So after this, this is the steps. These are the steps through which you can determine the difference between the distribution of the data which belongs to the category of transient fault or intermediate fault. So later on, the sensor node has a mean values that you have calculated. Then you calculate the overall mean of the n sensor node. So first we have calculated the individual sensor node mean values, and then we have calculated the overall sensors data that we have accumulated at the gateway. What is the overall mean? Then we will be calculating the standard deviations, so sum of square difference between n nodes. This will give us the spread of the data, how far it is away from the mean values. So it is kind of standard deviations that help us to identify the overall mean and the one sensor mean, how far it differ from each other. Then we calculate a degree of freedom between the n number of sensor nodes. So this value is basically the n minus 1. So the difference that we are calculating at first is the in between the sensor value, what is the difference. Then we will be calculating in between the distribution, what is the difference. So first we calculate between the sensor values, what is the overall difference. Then we calculate the mean square values between n number of sensors node. So it is basically a division of standard deviations with the degree of freedom. That will give us the mean square value. That is the mean difference between the census values. So you can understand this particular graph will give you the explanation for this. So like the values that we are having in this particular distribution will have these datas, and these datas will have this particular mean value, overall mean values, and each individual sensor value standard deviations from that particular mean value. So likewise, we calculated for all the faults, soft fault, transient fault, and intermediate fault. And this basically gives us the kind of understanding in between the data, what is the difference. Then we calculated in between the distribution, what is the difference. So within, first in between the distribution, and then within the distribution, within the data values, what is the distribution. So we also calculate in between and within the sensor value, what will be the degree of freedom. So utilizing the formula, it's a kind of formulations for the ANOVA. You can directly go and use this particular method to determine the in between and within the data, what is the difference. So to calculate that, there is a F ratio. So once you calculate within the sensor value, what is the difference, and when you and calculate the F ratio. So F ratio is basically between and within. This will give us the kind of important understanding that what would be the difference. And to analyze that, be using F critical value. This you can derive it from the F distribution table. So this F distribution table is available. You can just go and see what is the degree of freedom for in between and within. Utilize this particular diagram to identify this distribution table to identify what is the F critical. This F critical will help you to distinguish between the data as well as the distribution, what is the difference. So we can clearly determine this using this F ratio. If greater than the F critical values, then condition is satisfied. If this condition is satisfied, then we will say the null hypothesis is rejected, and it is concluded that there is a significant difference between the sensor value. So this will basically determine the difference between the sensor values. That is the null hypothesis. If F ratio is lower than the F critical, then if this condition satisfied, the null hypothesis, this is the alternate hypothesis, is rejected, and it is concluded that there is not a significant difference with the sensor values. So if this is the condition satisfied, then we can able to identify the difference between the faults. Either it is a transient fault or it is an intermediate fault, because these two faults will have a very close distributions. So this comparison basically determines the particular classification for the node at the pattern layer. So in probabilistic neural network, the pattern layer basically have this particular kind of distribution informations related to the different categories of fault. So if normal node is there, then R number of the times H0 is satisfied. Means null hypothesis will satisfy. Whenever it satisfies, it means there is no such faults. But whenever the null hypothesis is rejected, then there is a true soft fault we can determine. But intermediate and transient fault, there is a chance that 50% time this is satisfied, 50% time this is rejected. Then we will be saying that these two categories, intermediate and transient fault, a sensor may belong. So half of the time, if null hypothesis is rejected, then it is an intermediate fault. Otherwise, it is a transient fault, kind of. So how we train this particular model? So training of probabilistic neural network, we basically collected all these historical census data related to the different faults. So soft permanent faults, intermediate fault, and transient fault. So these three categories of fault we wanted to determine. So we have created a feature vector with these particular data, and historical data will have a kind of distributions that is representing the normal distribution to a sensor data, and that is a normal condition of the sensor. So we want to collect the data which is completely different from that normal distributions. That kind of data we generate for our feature vector. And this particular feature vector basically collecting different faulty census value. So we basically simulate these kind of problems and these kind of behaviors using various tools are there, like a COSA simulator is there, through which you can generate some faulty data. Or either you can deploy some real sensors. Within that, you can do certain modifications or kind of environment you can create that will generate totally different data. That is not kind of a normal data. These feature vectors, once you have it, that you can apply it to the input layer of the probabilistic neural network. And then the pattern layer will adapt according to this input feature vector, because pattern layer is already trained with the kind of data which is normally generated by the sensor, like a intermediate fault, transient fault, and soft fault. So pattern layer will have the information when data comes in this particular category, then and this is a kind of soft fault or intermediate fault or transient fault. So kind of we will training the pattern layer with the kind of different faults. So it will create a kind of Gaussian functions for each of these faults: soft fault, intermediate fault, and transient fault. And when we substitute the input vector, that is a faulty sensors data value, then it will start calculating the Gaussian function for each of these particular input vectors. So the data that we are providing as an input is a training vector, and partial of this data we will be using for the testing purpose. So training purpose, we will be putting this data as an input, and pattern layer is going to get adjusted according to that the distribution in a data according to the standard deviation and the mean value that will determine the kind of difference between these faults. So each neuron pattern layer basically compute the distance between the present input vector and the vector that we have provided as the faulty sensors data. And based on this distance, basically it will be identifying the type of fault. So distance basically subjected to Gaussian function, as we already know, the kind of mean and standard deviation that basically determine the pattern at the pattern layer of the probabilistic neural network. So you can easily correlate this particular diagram with the pattern layer functionality. So input vector which you have provided to this pattern layer, and pattern layer is generating these three different types of distribution for the type of faults. So this distribution will have standard deviations that basically determines the difference between the distribution of different category of fault. So this activation, so when you apply the data input vector, it will pass through all these particular pattern layer, and everyone will calculate the distance based on the standard deviation and mean, and identifying that whether this particular sensor value belongs to this particular type of fault or this particular fault or this one. So it will activate according to that particular input vector. And all the output that we have generated, basically applying the input vector, so and basically the number of input vector which you have applied to this probabilistic density function. So average of this all will be passing as an activation function to summation layer. So summation layer, basically we sum all and identifying the maximum one which is dominating to a kind of fault. So here when we do the testing for this particular fault classifications, we have just selected the sensors value that is coming all the time from the network that we have deployed for the environmental monitoring, and all of a sudden some data is not correct at all. So we have to classify which sensor has a fault. So we have created the exemplar vector for soft fault, for intermediate fault, that is a class 1, class 2 and class 3. So 3 classes are there. We have to determine which particular class the sensor has a fault. Then pattern layer is basically calculating this Gaussian functions, and based on the distance, based on the standard deviation, it will be basically determining the particular activation function. So basically it applied to every class of the fault, the input vector which we have submitted for the classifications, and when we will be substituting it, the average of these Gaussian functions G1, this is for class 1 and class 2 and class 3, basically activate the summation layer. And this summation layer once gets activated, we will be doing the identifying the which one is the maximum correlated with the type of fault. So we calculated with the G1 average of Gaussian function G1 class 1 is greater than class 2 or also with the class 3, then it belongs to the soft fault. If this is not the case, then intermediate fault, if the class 2 average of Gaussian function greater than the class 1 and class 3, then it belongs to the intermediate category, otherwise it will belongs to the transient category. So this is what the fault classification model that we have implemented using a probabilistic neural network on the edge devices to validate the census data is correct or not. So there are other major applications that probabilistic neural network has, like it is also applied in a class prediction of leukemia, central nervous system, tumors. So various kind of signals, EMG signal, EEG signals, where you can apply probabilistic neural network for classifications of type of different problems. Identifying the shifts, management of sensors set up in wireless ad hoc networks. So it is used at present for this particular purpose. Remote sensing, image classification, character recognitions. So there are many applications a probabilistic neural network has in IoT domain. So basically we required a kind of machine learning model which can take a small input data and train itself to classify a kind of faults. These are the resource constraint networks that you can utilize it for various IoT applications. Another work we have carried out on home energy management system using IoT. The purpose is to optimize the devices or home appliances at home using a special kind of sensing. So we will be using a wireless devices. So most homes and the commercial buildings as well as the residential buildings will have a Wi-Fi routers. So we will be using these Wi-Fi router for detecting the human presence in a one particular room or one particular location. So we are not using a multiple motion sensors which we locate at different locations inside a house, and that will basically operate the devices. Our plan is to utilize only the Wi-Fi router which we are using for internet connectivity. Also, we can utilize them for additional services like operating the home appliances like lighting, fans, and AC. Besides that, we are also taking a consideration of the environmental, what are the light intensities available, so harvesting of the surrounding environment, and then we will be operating. Also we will be taking the user considerations, what are the user preferences, based on that we can operate the devices. So these are the important applications in home energy management. So what we have done it, we have basically utilized the Wi-Fi channel state informations. Basically Wi-Fi devices using a Ofdm modulations. What is Ofdm? Is basically a orthogonal frequency division multiplexing, through which basically a single channel basically emitting the multiple subcarriers. So basically one single channel generates a multiple subcarrier frequencies. So modulation technique where we will be modulating the baseband signal with multiple subcarriers. So here is a no single carrier, here is a multiple subcarriers. That is called basically a sub-channels. So these sub-channels are called channel state informations. Basically, these sub-carriers carrying the signal strength to communicate from the source to destination. So your Wi-Fi router is generating this particular type of signal that will propagate to your device through multiple subcarriers. Why they have implemented this OFDM? So OFDM modulation is applicable to MIMO devices. You have seen some devices will have multiple antennas. When the device will have multiple antennas, there is a OFDM modulations in place. But that is not necessary, but most of the devices, Wi-Fi devices, will come with the OFDM modulations. So what is the difference between this normal signals? Normal signal basically transfer it with a single channel with a simple modulations with one simple carrier frequency. Here you will be having a multiple carrier frequencies, and that multiple carrier frequencies will propagate from the environment to your particular receiver. So when these particular signal is going to get struck with different types of obstacles, different types of object obstructions, we will be utilizing the signal strength change in a particular transmitted signal. At the receiver end, we will be observing what is the change in the signal, from which particular location this change may come. Based on that, we locate the person within that particular location, and then we will be operating the devices according to its presence inside a room. So applications are like detections, recognitions, and estimation. So these are the three important tasks we will be achieving using Wi-Fi. So with this particular diagram, you can clearly understand what is the intention here. We have one receiver, we have one router at the home for internet uses, and this router is keep on broadcasting the packets which a receiver is using for internet connectivity, and the signal is spreading all around the house. So this signal will get reflected from different positions, different places. It will reflect it from the walls, it will reflect it from the walking users. Okay, so whenever it will be reflected from the walking users, we will be observing the change in the signal strength, and the signal which comes direct line of sight will have the highest signal because it is not obstructed at all and it is direct line of sight. But the signal which is obstructed and coming from the multipath environment will have the change in the signal strength. Since these are not the static objects, they are keep on moving, so they will be generating a different patterns based on their movements. If he is standing or he is walking or he is sleeping, so it is basically changing the environment. So initially we will set up this particular experimental platform, transmitter and receiver without any object, and we will be creating a baseline database where we will be having the static environment signal propagations and what is the signal strength corresponding to those environment. So we have basically modeled this particular problem using machine learning, and we have implemented successfully for the home energy management. So initially we have acquired this CSI data from the routers to the receiver, and then receiver do the processing. So signal processing and signal feature extractions, time domain signal. And once we have the features, these features we will be providing to machine learning model to correctly classify the human object, and accordingly it can activate the devices on the inside the home. So what are the appliances? So we encountered various type of difficulties in this. Basically the sparsity number of Wi-Fi access point. We will be basically operating with one Wi-Fi router to try to identify in a different room also. If the router is present in the hall, we wanted to detect the human presence in the bedroom also, in other part of the house also. So it is kind of difficult problem because a lot of signal processing and lot of feature extraction techniques machine learning training is required to identify correctly the presence of the human object. Predictability and dwell time, so how fast it can basically do this kind of classification and how far it is correct. So we will be also dealing with the kind of challenges. Need of standard protocols for HEMS. So this is also kind of problem because the available hardwares and available devices all is basically not supporting the CSI. Very limited hardware will have the capabilities to generate this CSI data, which we can sense it and use for our research. So very limited hardware, very limited protocol that we can apply for the home energy management. That is why we also come up with this particular solutions that could detect the human presence. Adaptation of such technique by public is also a major concern because we are not knowing when this particular product, when we launch in a market, whether it will be going to get success or not. So kind of we will be also analyzing from the market perspective for commercialization perspective. Vulnerability to power failures. So this is also a kind of problem because Wi-Fi routers required the power to operate, and our receiver is also required a power to operate. When power is not there, whether this particular system can operate. So we should also monitor these kind of other important problems. Data collection is another problem that we faced with this particular kind of occupancy detections. Sensor deployment is also a major concern where we should deploy so that we can get optimal output for occupancy detection, whether the person is there or not. So we should also plan it according to the signal strength, how spreading the signal is uniformly distributed in the entire house. What are the obstructions that could obstruct minimal in a kind of placement? That is what the another important aspect in this occupancy detections for a home environment. Because lot many obstacles are there, lot many devices are there that can create a kind of multipath environment, and sometimes you may not receive the signal at all at the receiver because it is multipath multiple times. Accuracy and user comfort, so how it will be adversely affecting the user comfort. These are the other challenges that we also pinpointed in this particular problem. Then effect of environmental conditions, energy efficiency and battery life, and device heterogeneity and Wi-Fi sleep policies. So this is also important because Wi-Fi device is not a single Wi-Fi that is operating in your house. Maybe the neighboring house will also operating a Wi-Fi router. That signal can also come up into your receiver and create a kind of misclassification. So we have to deal with all such issues in order to correctly identify the occupancy inside a house. So external Wi-Fi signals should also be avoided in processing. So we propose this kind of solution where we kept a Raspberry Pi board and Node MCU module, because Node MCU module uses a Wi-Fi chip that basically releases the CSI data. Only the problem with the ESP32 module is that it has a single antenna, and we required a multiple antennas to sense the all signals rather than few CSI data. But we have managed with ESP32 to correctly classify some of the activities related to the occupancy. And we also light sensors and other sensors that could help us to operate the device in a home applications, like a light bulb when you can operate. So if the daylight is enough and it is available in the house, we will be sensing it with the light sensor and not operating those devices. So kind of smart scheduling of those appliances when heat surrounding environment is cool and the adequate requirement for a comfort as per the user preference is available, then we will not operate the device. So kind of smart home applications where we will be using this IoT solutions. And once the data is generated, we basically trying to identify the different activities. So we will be first detecting the occupancy of the person. Then daylight models, we will be looking at the daylight harvesting, how effectively daylight is available in a house and how frequently we require to operate the bulb, when to operate, when not to operate. Weather forecastings, then user preferences, and then we will be using historical data also in order to do this kind of management of the home appliances or the devices for the better utilization of electricity. So basically the preliminary analysis we have tried with the Wi-Fi RSSI is a received signal strength. It is available with every RF devices, but only the problem is that RSSI data is very much vulnerable. Basically, it is very much affected from the surrounding. Even if the person is not there inside a house, it is keep on changing. So it is not very stable way of detecting the occupancy. So RSSI data, we are trying to model it with a distance. So it is not basically giving us the correct observation for the signal at one particular distance. So we basically tried these experiments multiple times. We observed at 1 meter what is the signal strength, 2 meter what will be the signal strength, and when we will be monitoring at the different distances, we are not getting the consistent signal strength. It is keep on changing without any obstruction, without any object. When the obstruction is coming, then it is creating a lot more change that is even not easy to process it what distance the signal is affected. So this model we have just dropped, but we have done some preliminary exercise with this particular kind of sensing. We have basically created a few finger points inside a house. We thought the RSSI signal at this reference point, if changed, then we can locate the target within the house. So we selected few reference point and trying to create a fingerprinting to this particular house with the signal strength. So we observed that observation with the signal strength, mean, mode, median. So preliminary analysis we have done through statistic. We observe the variations, variance. So these reference points, we have monitored the changes in the signal strength. Then we analyze it with the walking user, how the signal is going to get affected. So without any walking user, we are getting the kind of signal. But one user is walking, then we are getting kind of signal. So it is not very much different. And then two walking user, there's a kind of different observation. But all these observations were taken when the object is in between the line of sight. Whenever he is away from the line of sight, the observation is totally different. So it's very difficult to monitor these changes. So we have done a preliminary exercise with RSSI signals. We observed with the one user, you can see the mean value is 39.360 when no user is there. But when one user is there, then also mean difference is not very high. So kind of difference is not very different. They are kind of very close. And when we use these kind of data, these kind of RSSI measurements for occupancy detections, it is also always be going to give us the wrong predictions and the wrong identification. Median, you can see also here is the with no user and one user, there is no difference. Mode also will have no differences. Variance, there is a kind of certain variance you are observing, but this data kind of not helping us to identify the occupancy inside a house. However, we still apply the feature vector that we have acquired through Wi-Fi RSSI data and apply on random forest, multi-layer perceptrons, various algorithm. We have analyzed the performance, and it is giving us the 96.66% accuracy, and that is also with the various misclassifications. Sometimes correct classification, sometimes very wrong classification. So we are not justifying the outcome with the help of Wi-Fi or SSI. So we move to the CSI. So CSI data we have collected from the ESP32 module. It is a very cheap module. We'll have a Wi-Fi adapter on top of it. That is basically a non-MIMO device. So it has only one antenna to receive the signal. So we kept one router at one end and this ESP32 at other end. And the signal generated by the router using Ofdm modulation. So subcarrier is following a different path inside a house. And finally it is receiving at the receiver. Now we have to detect where the occupancy of a person is there, and according to that we are operating the devices, a lighting system, fan systems, or air conditioners. So here you can see a clear distinction in a data. The data basically generated in the form of subcarriers. So one subcarrier, two subcarrier, likewise we will be having almost 64 subcarriers using this particular type of sensing. So walking user, we will be getting a 64 subcarrier data. So you can see every individual signal is basically one subcarrier, and there are total 64 subcarrier. That is what this clumsy data we are getting. So this is a feature signal that we are getting from walking user. Then standing user, we are getting a kind of feature vector. Similarly for sitting user, we are getting a kind of feature vector. So all these data will have a distinctions. That we have done it with a simple processing. So we acquired this CSI data in a CSV file. Then we have applied some data processing. So some noise cancellation filters we have applied. Some subcarrier will have no data. They are just null. So we have just avoided those subcarriers, and then we have processed this data. So outliers within this particular subcarrier, we have removed it, and the subcarrier which has the data, which has the multipath reflections of the objects and the obstructions, we have taken into the consideration for analysis. So how we basically apply this? The feature extraction process, we basically apply the process of identifying the occupancy. We have selected few reference points inside a house. So likewise, we have selected one position, two positions, three positions, likewise we have selected. So these are our ESP32 modules on these locations. Because one module may not be enough to detect the occupancy related to the person. And then we kept one Wi-Fi router at a distinct locations. So this Wi-Fi router is keep on emitting the CSI data, basically for internet connectivity, and these data we basically acquiring it. And on these reference points, we are trying to monitor when the object is coming in this particular place, he might be obstructing the communications, and the signal which travels from these locations, it is going to get affected from these reference points. So these reference points are the indicator that the human might be present in this location, this location, this location. So we are creating a kind of grid environment inside the house. And each grid is a kind of location which we will be determining with the help of reference points. So we basically aggregate subcarrier mean absolute deviation in single packet, and then mean absolute deviation along the subcarriers. So we are also applying over here the Anova techniques to distinguish between the data. And then correlation coefficient, we will be determining it. So here, the extracted features from the CSI data. So here mean variation of subcarrier amplitude aggregated from these packets. So if you can look at closely, the empty room, you will be getting the signal strength up to 40 dB something around, and the kind of clearly distinguishable signal we are getting. And for the walking user, we will be having a kind of signal that is also very, very easy to distinguish. Standing user will also have a distinction that could also be detected very easily. And for sitting on sofa and kind of will also give a kind of different variations. So as close the object towards the transmitter, then the variations will also be very dominant. And we can easily determine it by looking at different reference points, what are the observations. So we have monitored it with the different locations setting the transmitter and receivers, and we are able to detect the clear distinction in all type of activities which occupancy will have. So walking user, we have kind of all the reference point, the distinctions, we are observing it and we are keeping it. Similarly, for standing user, we will be clearly seeing the distinctions in a signal. And for sitting user, we'll also have a different distinctions. And this has given us the kind of motivations to detect and clearly distinguish between the type of activities. So we can simply partition these signals based on the type of pattern that they have generated. Now the question comes how we can determine all these different classes. So we apply a kind of machine learning techniques in this particular domain and trying to identify the particular pattern. So these patterns we are trained, so we can use either probabilistic neural network, random forest, decision trees, various methods are there, various models are there. We applied all of them and we got almost 86% accuracy for detecting the different class of activities a occupancy will have. And accordingly, we operated the devices to that respective locations. So this is a kind of work which we have done it for occupancy detection in home energy management purpose. Another work, actually this is a work is funded by DST where we are working on managing the aquaculture environment. Basically, aquaculture is more dominating in today's scenario. We will be having a fish culture, we having a prawn culture, shrimp culture, we have a pearl farming cultures. So various type of underwater agricultures we are doing it. But still we will not have technologies to support those aquacultures. And the area which we have targeted is a pearl farming, is a kind of freshwater pearl farming where we wanted to grow a freshwater pearl. And to support that production of better quality, we are integrating the IoT subsystems. So the main purpose of this particular system is to monitor the water quality parameters, train the systems according to those water parameter systems. When they deviates, we will start actuating the devices so that they can regularize the water parameters. So in this particular problem, we will be taking a few sensors like pH, dissolved oxygen, TDS, temperatures. And we have scheduled the aquaculture monitoring and maintenance with certain time period. Like morning time, the pH value is very high. And daytime dissolved oxygen is very high, but at night dissolved oxygen may reduce, pH may increase. Kind of variation will come when the aquaculture farming you do, either fish farming or a pearl farming. The kind of problem we will be facing. And ammonia is the biggest problem in underwater. So to deal with this ammonia, we are making a kind of system based on data analytics. We are applying some machine learning techniques to determine the change in certain parameters. Based on that, we are operating the actuators to remove the excess of water or adding some more waters, to operate the aerations to supplement the desired oxygens, biological oxygens. We are also using some biofilters to remove the water from the tank at regular basis to remove this ammonia content from the water and reuse this water. So biofilter is a part of recirculative aquaculture system. And various actuators we required, like solenoid valves, motors, water pumps. They're also a part of complete design. In this particular work we have done it, and we have implemented this whole entire design for IoT, from the physical domain to network domain to logical design. So this is a kind of work I'm representing over here. The proposed, basically the system we have divided in 3 categories: physical design, network design, and logical design. In a physical design domain, we have used some beagle-bone blackboards. These are the IoT communication boards. And we have selected based on the parameters, like how many peripherals these particular board will have, what is the processing capability it has, whether it has an inbuilt database options like a space. So we have chosen this particular platform, and we connected various analog sensors. We also connect some analog to digital converters for better precision, because analog sensors will always give us the kind of variations that is more critical to be monitored in a very precise manner. So analog sensor, if a low resolution ADC if I use, then the signal variations will come after a certain period of change, and that I cannot take for better management of aquaculture. I required a precise measurement. That is why I have used a 16-bit ADC externally to sense the water parameters like dissolved oxygens, pH values, TDS values, and transform it through this ADC to more precise values. And this will give us the kind of variation that is very, very small. So to the power of 16. And the reference voltage is 3.3 volt. If you can divide it 3.3 by to the power of 16, you can get that kind of accuracy, that kind of resolutions out of this ADC. So we have taken various sensors probes connected with this particular edge device. This is our IoT edge device. We have also provided the power backup systems to provide the power in case the power is not available. In a network design, we basically integrate one router that is a kind of gateway for our communication with cloud systems. We also integrate one fog node in a network that is also connected with the gateway. So the processing that is essential to timely monitor the activities within the water parameter or aquacultures that needs to be monitored and maintained properly on time. We have kept the analysis at the fog node, and there we have running a local server that is operating at the one IP addresses that we have assigned it from the gateway. So gateway will have 4 ports. Each port will have a different IP, that is a class C IP. So one IP is dedicated to the fog node, and that IP we can operate it from the local network. So if I connect my mobile with this Wi-Fi, I can able to access the particular website that is running in fog node, and I can operate and I can look at what are the water parameters are there, how it is sensing, what is the analytics that is keep on running on it. And this particular TP-Link router will also support some VPN services. So we are running one VPN server here to securely communicate with the cloud in a public domain. Analytics algorithm we use basically here model tree. Model tree is basically very good to give a kind of prediction in real time, and it also supports a kind of very effective controls on the actuators. So we have used the model tree, but we have analyzed a different algorithm for water parameter analysis, and model tree was the most optimal one we identified in our analysis. This is what the design that we have done it with the Django framework, where we have used the backend MySQL databases. We use Java scripts. We have used chart.js. Chart is basically giving us these kind of visualization of the data. And the whole front end we have designed with a Bootstrap and HTML5. So here basically we kept all the data visualizations, and some of the other settings we kept it like a device setting. So recalibration we can do it from the remote locations. So similarly, the sensors testing, we can apply some test vectors to monitor whether the census data is correct or not. And kind of some device authentications also, we have a API key. So every device, when interested to connect with this cloud system, they have to get registered with that API key. So that API, they can use it and write it into the device. Then device will start uploading the data and you can visualize it over here. So we have implemented some security features also in this particular design. So few analysis we have done it on the data, what type of data, what is the correlation between the data. And based on that, we have selected few important parameters that is most affecting to the water quality parameters, like a dissolved oxygen, pH and temperature. So these three parameters we are taken into consideration. Dissolved oxygen is the motive of our system to detect how much it is changing, and it is also having a relation with temperature and pH values. So we have considered these two input vectors to determine this vector. Similarly for pH we use this DO and temperature input vectors. The result we have observed here, like DO predictions, we have applied some algorithms like random forest, model tree, M5 and gradient boosting machines, and we obtain a very good accuracy with the model tree 0.963 for DO predictions, and for pH predictions very high accurate. So this is what we have practically implemented, and the other work which we are planning it on this particular anomaly detection in IoT networks. So for that we basically have a kind of system we implementing like a FreeRTOS. Here we basically having a normal microcontrollers. They are running the real-time operating systems, and this is what a kind of industrial critical system. So they are operating some devices, actuators, and their intervention in their operations could have a drastic impact on the supply chain management. So we are planning to make secure these particular bottom network. And to do that, we will be having a fog node in the network. These fog node running an algorithm called based on statistical learning. So basically these fog nodes are connected with these FreeRTOS systems, and they are sensing the processing, memory utilization, network utilities, all real-time information in time series data. So it is storing the time series database over here, InfluxDB. All the fog node will have InfluxDB, they are connected and sensing the utilization of processor, CPU, and other peripherals. And based on those important input elements, we will be designing our machine learning models. So we are planning to use probabilistic neural network also, because it can map the kind of change in the particular peripheral operations. And there are certain master nodes also we are keeping it that basically sense the kind of network attacks. So if fog node is getting attacked, then it can be isolated from the networks. So kind of model we are implementing it, and very soon we will be going to deploy it for our smart applications. So with this, I close this session. If anyone has any doubts, then they can ask. Thank you. So anyone has any doubt, they can please.
Network connection. Okay. Thank you, Munesh sir.
for sharing the knowledge with us. It was a wonderful and nice session.
Yeah, thank you. So any participants will have any queries, because the first session also I have completed and taken over of period time. So that's what I think some participants may have questions they can share.
Participants, please, you can ask any queries.